what can we do about the fact that cloud is not a good option when we need results quickly. So it is there that this fog and edge computing can make an impact. So if you see in this slide, we have different layers of hierarchy, right? And at each hierarchy, you have kind of a computation and storage capability. At the top, you have the cloud service provider. So this is a case of smart transportation. Okay. So you can have different kind of clouds. You can have a cloud of your manufacturer. So these days, at least in the West, smart cars are very popular. And I'm sure in India also, next 5, 10, 15 years, they will be quite popular. So whenever you buy a car, but the manufacturer will also have their own cloud. There can be a cloud of the traffic services and other kinds of cloud services. And then below you have these different layers of fog nodes. So essentially, when we ask what a fog node is just like you can say a small part of a cloud. So it provides similar services to the cloud, but on a smaller scale. So to give you an example, in the cloud you can have like lot of servers, lot of supercomputers, which are very fast and which have almost unlimited storage. But in a fog, you will have like smaller devices, like maybe even a Raspberry Pi or a gateway or a router. So as compared to the cloud, they will not have that much compute power. But the advantage will be that they are located very close to where the data is generated. So if I have a smart car, it's generating a lot of data, and I have a fog node maybe within the car itself. I may have a fog node on the highway. So again, the distance between that and the vehicle is very less versus the cloud. So which means that for some of my real-time jobs, applications, I can do the computation and even storage in the fog nodes. So here again, within the fog, you can have different hierarchies. So as you move up in the hierarchy, your capability improves. Okay. You get faster computation, more storage. But the downside is your delay also becomes higher. So as such, fog computing was conceived to address applications and services that don't fit very well with the cloud. So applications that require low and predictable latency. Other advantage of the fog or edge is that it is distributed. So distributed means that you can say it can be more resilient to failures. Cloud is more or less a central architecture. Right? You may have seen many times Google is down. You can't use it. This one I can say. So as such, fog is not a alternative or not a competitor of the cloud, but rather it increases the capability of the cloud. So which means that fog and cloud are meant to be used together and not in place of each other. So then the idea is that you have to figure out, you have to partition your workload and figure out what goes on the cloud and what goes on the fog. So they share the same resources, networking, computation, storage. They share mechanism, virtualization, multi-tenancy, and so on. So just like you can have containers in fog, cloud, you can have containers in fog also. So in a way, you can say that the fog brings the cloud closer to the users. That's one way of looking at it. So here we see, for an application, the kind of latencies you need. And for low latencies, executing at the fog will be a better idea. High latencies, cloud is fine. And then you have in between, so therefore, when you have a hierarchy of fog, you can figure them out. So the idea is for fog is to minimize latency, definitely very important. to conserve network bandwidth. So now what you're doing is good part of the traffic you're diverting to the fog, which will free up the bandwidth, cloud bandwidth. We can address security concerns. We know a lot of users are they don't like that their secure information is in a third-party cloud data center by Google and California. So using fog, we can address that. You can maintain a fog data center within your premises because it's a small device, cheap to get. Reliability, of course, we talked about because the fog network is more distributed, so it's more reliable. So idea is to move the data to the best place for processing, whether fog or cloud. So today we talk about two problems, not three. First one is more theoretical, real-time security-aware scheduling on network edge. Second one is a bit more applied, fog-based over-the-air software updates in smart vehicles. So let's start with the first one. So here we are looking with proposed real-time scheduling algorithm for fog cloud. This was one of the early works, and this was done in collaboration with artists and Auluck. So again, here we're just showing some applications for cloud and edge computing. So as you move towards the right, extreme right is the cloud data center. Right? So unlimited computation, fast computation, unlimited storage, but high delays. On the extreme left side, you can have fog nodes, less computation, less storage, but very low delays. So you can see the trade-off here. So this one we can. So this is just some terminologies. Fog nodes are also called as cloudlet or like small clouds. And here we call each cloudlet as a MDC or micro data center. Cloud is CDC or cloud data center. Just some terminology we are using. So here our idea is we want to accomplish two main things. The first is that we want to offer low response time for delay sensitive applications. So if I have a job with a tight deadline which needs to be executed really urgently, and if I send it to the cloud, so it may not be good news. So can we run such applications on the fog nodes so they can finish earlier? That is one idea. And the other is also looking at the security constraints of applications. So if I'm dealing with some sensitive information, then I'm not sending it to cloud, but I'm sending it to fog. So put it very simply. So last one I will not talk about because of time, but this one also we did. So the idea here is, so we propose this algorithm RT-Same, which supports both batch and interactive applications. So generally interactive applications need results very quickly. So those are good candidates for running on fog or edge. Batch applications are long running and generally not urgent, and those can be run on the cloud also. So we support both batch and interactive applications, and taking into account their deadline and security constraints. So we simply choose between an MDC close to a user and a distant cloud data center by looking at the network delay, deadline, the security tab. So this is our basic architecture, quite simple. Users with their devices, the MDCs, and then the CDCs. So this is one this is a sequence diagram which shows the kind of messages that go back and forth. So if I have a device and it wants to run a job, it can be sent to the MDC. Now if the job can be accommodated there, then an acknowledgement is sent back. Then the task is submitted, task completed, result sent back. Scenario B, task cannot be accommodated in that MDC. So then, it can be sent somewhere else, to a cloud if it's a batch job, or to another MDC if it's a interactive job. So like that, we can have different scenarios and different sequence diagrams for this. So here to look at the security of jobs, we assign them certain labels or tags. So for jobs, we have P for private, SP for semi-private, and PU for public. And likewise, for the execution resources, whether it's a fog node or cloud, we have highly trusted, semi-trusted, untrusted. Department is operating or you are operating, so you have control over it. Semi-trusted could be the one, maybe a fog operated by your institute, which you still trust but not as much. Untrusted is anything in public domain. So the idea here is based on the labels, try to assign the jobs appropriately. So which means if I have a public job, I only assign it to a highly trusted resource. Those are my kind of resources. If I have a public job, generally untrusted would be a good place for it. But we also consider highly trusted, semi-trusted if space is available. Otherwise, generally it goes into untrusted. So this is just a mathematical modeling. I won't spend too much time. Set of cloud data centers and set of MPCs, interactive jobs, batch jobs. Just some mathematical modeling. This is how we arrive at the communication delay. Right, so let's say if I'm sending 100 megabytes of data, if my bandwidth is 50 Mbps, it takes 2 seconds, 100 by 50. Start time plus execution cost plus communication delay should be less than deadline. Communication delay between the job and the fog node. Just a bunch of equations. This is a deployment cost, so each fog node will have a cost to maintain it. So you will need electricity, you will need cooling costs and so on, other kind of costs. That has been modeled. So the idea here is we want a good performance, but we also want to use the fog nodes judiciously. We want good utilization. This part we can run. So we get that by modeling the utilization. So we want the utilization to be as high as possible, but at the same time performance should be good also. So rather than having 10 fog nodes with only 5 to 10% utilization in each, maybe I just need 3, and then utilization is 50-60%. So less fog node means less maintenance costs. So system utilization. So our main idea is to maximize what we call a success ratio. So success ratio is number of jobs that meet the deadline divided by total number of jobs considered. So success ratio is 90% means 90% of jobs meet the deadlines, 10% do not. Success ratio 50% means only half meet, half do. So we can see why using the fog can improve the success ratio. Because if you send everything to cloud, if you don't have fog, then the jobs which have tight deadlines, they will miss the deadlines. You can't do anything. So which will bring the SR down. But if those can be run on the fog, it can increase your success rate. The main idea is that. Okay, these are some equations which we can. So whenever you assign a job to a MDC or CDC, you have to make sure that enough spare capacity is there. Cloud generally are mostly, they always have capacity. Not that important. So this is the algorithm. So as such, to put it simply, we have two kinds of jobs, interactive and batch. Okay. Interactive are the ones we need quick responses, and they generally run for a short amount of time. So small jobs for which we need quick results. Batch jobs, they take longer to run. And each of these categories of jobs, they can be private, semi-private, or public. So we have different options. So what we do is we look at the job category, we look at the security tag, and then we decide where to schedule it. So for example, if it's an interactive job with private tag, we will run it on the local MDC. Local MDC means MDC that is run in my room or in my floor or something. So for interactive with the semi-private, private runs on local MDC. Batch job which is public, I can run it on the public cloud. So like that, various combination and combinations are there. I may have a batch job which is private. So then I may need to think of maintaining a private cloud in my premises. It is also possible. Yes, as far as possible, try to run the interactive jobs on the fog nodes. Okay. And if you do that, your success ratio will increase. So this is the simulation results where we compare with another algorithm. IFOG score. So this one also uses fog and cloud. So this is the workload trace which we consider. These are some values which we consider. The values can be changed based on application requirements. There will be some trends. Capacity of CDC will always be much larger than capacity of fog. Fog may just have like a Raspberry Pi. CDC may have like a supercomputer. And the communication delay between user and fog will always be less than between user and cloud. So these kind of trends will be there. Otherwise, the numbers can be varied depending on your area. So these are the metrics which we examined. This is a simulator. So here we see effect of including edge or fog capacity on performance. So here we are comparing our algorithm with the cloud only. So cloud only, there is no fog, everything goes to cloud. So at once we see that in the cloud only approach, the success ratio is much smaller. And reason for that is very simple. If the job deadline is tight, you don't have a lot of time to run it. And by the time the job reaches the cloud, already too late. So you will see that for CDC only the SR value will always be lower. And here we look at deadline factor. So how tight or loose the deadlines are. So if the deadlines are very loose, then we can see it doesn't really matter whether it is on fog or edge. Because anyway you have a lot of time. But if deadlines are tight, then having a fog helps. This is task load, how many jobs you are adding to the system. So more load means performance will go down, finite capacity. And this is the communication delay factor. So again, if you increase the delay, performance will go down. Because more delay means jobs spend longer to reach the fog or cloud. Because they spend longer, they start later. Because they start later, they end later. Deadline more. So here, same results, but we are using the other fog algorithm. So here generally again we offer better success ratio. And reason for that is this other algorithm this is not a real-time algorithm. So it doesn't look at deadlines. But the trend of the results will be the same. Our success ratio will be higher. So here if we increase the number of fog nodes, what will happen? So more fog nodes means more computation capacity. So performance should improve. That is what is happening. What kind of jobs we have also has an effect. So here we see 0, 100, so which means all the jobs are bad jobs, no interactive. So when all jobs are bad jobs, there won't be much difference between cloud and fog. It's quite comparable because there is no tight deadline. But still fog will do better because at least some of them will absorb. But if all the jobs are interactive, then tight deadlines. So again, what do we conclude from this? The communication delay, communication latency to the user devices is a major problem or bottleneck for cloud processing. So because of the large communication delay between the user and the cloud, the real-time jobs, they will not do very well. So the edge devices, they can help there. And it is intuitive to execute such real-time applications at the edge of the network. So given this, we propose an algorithm which looks at both the performance by performance I mean deadline or success ratio, and the security. Simulations comparing RT-Sane with iFog store and cloud only or real workload data. These two traces shows that RT-Sane offers better performance with high value of success. So that is first one. So next we look at an application for fog computing. This was done with colleagues from IIT. So here we are looking at faster over-the-air updates in smart vehicles using fog computing. So a good example is the updates in your smartphone. So in your smartphone you have various kinds of updates. One can be an update of the OS kernel itself, or you can have updates at the application level. So generally when an update is available, you launch that update, and most likely what is happening is you are getting that update from the cloud, from Apple's cloud data center or Google's or whatever it is. So similarly, you can have updates in smart vehicles also. And now some of those updates can be time sensitive. So for example, let's say driving your car and there's a huge storm or rainstorm like that coming up. They started these systems abroad, like in 50, 20 kilometers. So you need to be alerted. So, or there's some, some attack is happening, some war zone or something happening like that. So in those cases, those kind of alerts you need extremely quickly. So you don't want to depend on the cloud for that. So what we say is for those kind of updates, why not get them from the fog? So we already know that we have this fog layer which sits between the cloud and the users, and the advantage of the fog layer is it's quite close to the users in terms of physical distance. So if you want some processing done quickly, fog layer can be done. So as such, smart cars are highly computerized. In fact, if you see uh, which device has the most amount of computers in them, it's by far it will be a smart car, nothing else. So we can see some examples. So here, there's a company called Tesla. You may have heard of Elon Musk, right? So here the idea is in these cars, a lot of the functionality is given by software. So it's not purely a control or mechanical system. Software part also comes in. So they're combined together. So you can see, so they have a dashboard, just like in a mobile phone. From time to time, you get these updates for your vehicle. So what can they be like? Automatic wiper improvements. For that. Automatic lane change improvements. So if you want to change a lane on the highway, you're not sure where the vehicles in the other lanes are. So your car will tell you. Well, it has cameras and those kind of things. It will capture that and then tell you that this is a good time to change lanes. Otherwise, it will warn you that the car is close by. Don't change lanes right now. It may even tell you that you can change lanes in the next 4 seconds. Automatic lane changes have been done to make lane changes with more confidence. When adjacent lane is detected to be open, automatic lane changes will initiate faster. This will get the update. Some more updates: automatic emergency braking, autopilot speed limits, climate control, screen display. So many kinds of updates you can get. So some of these updates may be more time sensitive than the others. So let's say there's an update to improve the screen to give you a better visual experience. So that may not be that time sensitive. You can maybe wait for some time to get it. But if there's an update on automatic emergency braking, so you don't want to wait for this one. You want to get it quickly because it's a safety issue. So the idea here is if an update is time sensitive, let us get it from the form. So this is you can see 152 million cars. So at 2020 is gone. I don't know if they reached that number. Generating 11 petabytes of data annually. So you can see probably. I had another slide which tells you how much data the vehicle generates. You can see every day, and this is only one car. Supposed to be 152 million of these, or even more. So because generally they're grabbing images and video, and we know that they take up a lot of memory. So then when you have this much data, if some of it can be processed on the fog, you would get the results quicker, and some of the load from the cloud would be taken also. So here you can see the time thing coming in. 60% of collisions can be avoided with half a second warning. 90% of collisions could be avoided with full second warning. So if you can get that information even half a second quicker, it can have a big impact. So can you get it by processing at the cloud? No. So here our idea is, I just explained that try to get some updates from the fog. What that will do is you just get them on your device quicker. So think of it as downloading an update for your mobile phone from a fog device located here. So you would have experienced if you get the update from Apple or Google, how slow the process is, very slow. Performing an end-to-end latency analysis involved in downloading an update. So we try to model what happens when we get the update. The main chunk of the time when we have gone in downloading the update, but there are other delays also. Studying the effect of vehicle mobility on update process. So if I have my mobile phone, I'm getting an update from this fog node. If I go to different building, what will happen? So sort of what happens in our mobile calls. We have a process called handover. We move from one coverage area to the other. So that is called a handover, and we studied that these handovers, they add a lot of overhead. So if we can minimize handovers, we can improve performance. So this is how we modeled it. So you see two different kind of fog nodes. One kind is the stationary fog node, which is shown using the tower. So when you're on a highway, you can have fog nodes that specified in towers. So that is one kind of fog node which is stationary. Other kind of fog node can be in the smart vehicle itself. Smart vehicles have a lot of fog node. So the second fog node is mobile, moving around. And then of course you need the cloud as well. We did explain that the fog is not used in isolation. It is always used with the cloud. And then these colored circles, they show the coverage area of a fog node. So there are 4 static fog nodes, 4 coverage areas, different circles. So there is just some modeling which. So for updates, either you can do auto update or user demand, just like with mobile operating systems. This is just OT update manager, we can skip through that. So this is the algorithm for software update. I won't go too much into it. This is for mobility management. So here what we need to do is, so let's say I started the update with one fog node, and then if I move to a different coverage area, so then let's say my update was downloaded 60%. So then when I change the coverage area, what happens? Does that 60% go to waste again? Again I start from 0, or when I go to the new fog node, it remembers that I was at 60% and then I get started at 60. So that kind of thing is handover, which we look at. This is again we are just modeling the formula. So this XI, what this XI is, the part of the software update which I get from a fog node. So if I end up getting my update from 2 fog nodes, then I will be n will be equal to 2. So the equation becomes sigma I is 1 to 2 xi. Simply x1 plus x2. x1 is the part of the update I get from fog node 1. x2 is the part of update I get from fog node 2. So it could be more or less. So we want to minimize this. So if I add up all the parts, I get the total update. So this is our setup. So we this is the software update framework we used. So if you again there's a GitHub link for that. So you need to get this software on your desktop or wherever you're forming it. So this is specifically for Uptane. It's called Uptane, and it's specifically for software updates. So here what we had was for cloud we used Amazon's cloud. We had it on a server, and for the vehicles we used laptops because we could move them around for the mobility. Since we didn't have access to smart vehicles, so we had two laptops simulating two vehicles. And the form node we got we simulated using a Raspberry Pi device. So the Raspberry Pi is in the same room as the lab. It's almost local computation. Cloud is Amazon Cloud. There was Bangalore there. And the vehicle, the laptop vehicle. So here what we see is software size versus total update time. Total time to get the update. So we see that when I use a fog node, we simply get the updates quicker. Why? It's very simple. Because when we get the update from fog, the communication delay part is much smaller. And the other if I'm updating WhatsApp versus if I'm updating the whole kernel going from iOS 11 to 12, the second one will take more time. Simply more data to do. So here we try to increase the number of vehicles in the coverage area and see the effect. So there was not much effect, more or less constant, which means that our computation framework could give a decent performance even with 5 vehicles. So we could not test for long more than that, but one can assume that when the number of vehicles increases by a lot, performance may go down. And again, fog gives a smaller time than cloud. Second one, we looked at different components of the software update. So here we have 4 scenarios. So one is static dynamic. So static means when I'm getting the update from the stationary fog node. So let's say there's a fog node in my parking lot. I park my car. I stay there. I get the update. Dynamic update. I'm going on the highway. I'm getting the update, and I have fog nodes installed after every, let's say, 1 kilometer. That is a dynamic one. So generally, you can see for the static, I have 3 parts. One is communication delay. So some messages go back and forth. And for that. And then the actual propagation delay. And then the bulk is the update time. So for the static part, we have only 3 components. So SU static fog, SU static cloud. So this one we get it from fog, that from cloud. So cloud it will be more. And then in dynamic we have 4th component, which is the context transfer. So this is the handover part when I am moving from one fog node to the other, and my update is saved and then it's resumed on the new fog. So every time I change from fog node X to fog node Y, I have what I call a context transfer. Like in operating system, we have context switch when I go from one process to the other. So those are the context transfer, and we will only see them in the dynamic one, not in the static one. Because no handover in static, I'm getting the whole update only from one fog. So there's no question of changing fog nodes. So here we look at the performance with and without the ILP. So the ILP is the algorithm to minimize number of handovers. So this can be done in many ways. The way we look at it is, if we know the route of the vehicle beforehand, many cases we do know. So if I'm going to work from my home, it's going to be same route every day. Maybe there may be 1 or 2 ways to get it. So if I know the route beforehand, then I can find out, where or on which route the faster fog nodes are, and then I can route through those. So if I route through the faster fog nodes, faster means more powerful fog nodes. So then if the fog node is more powerful, which means I'll get the update quicker. So the quicker I get the update, the chance of doing more handovers reduces. If all the fog nodes I encounter are very slow, then I may have a chance of having a lot of handovers. Because every time I'm in a coverage area and the fog node is slow, I won't make much progress in getting the update. So top one is number of handovers. So without ILP and with ILP. So with ILP you see the black one, the number of handovers is less because that's what it optimizes. And that directly translates to smaller number of handovers translates to smaller overall update time. Because every time I do a handover, I have this context overhead, so which I have to pay. So as such, here what we looked at was, so at present, this I'm not sure, maybe, but at least a couple of years back when you wanted to, you had a Tesla and you wanted to get the updates, you had to go to the dealership. So they will hook you on their network and you get the update. Now I think they started to push the updates over the air. We call this OTA updates. So where you get the update from the, just go back to the case study. Yeah. So you either get the update from the manufacturer cloud, or as we are proposing, you get it from the fog devices. So if you get the update from the fog devices, you get them quicker on your vehicle. And plus, it's although we did not explore it, it can be more reliable also. Because let's say if the cloud is down, so then you can get the update. But if you're getting it from the fog nodes, if one fog node is down, because it's a distributed setup, it can be rerouted from another fog node also. But we don't explore that, but other papers do. At the end, so the main idea is the updates which you need quicker, you get them from fog nodes. And other thing we looked at was we assume that the car can get the update while it's moving also. So these were papers for the first work. We had a conference on it. These were the papers from the second one. Nothing at the end. So mostly this was all done by our students. So we just guided them with our collaborators. So again, just to quickly summarize, fog computing is a good option when you want or to execute real-time jobs or jobs for which you need quick results. So it's kind of like a micro cloud, you can say, micro cloud. And, now a lot of applications are coming, and It also fits well with the IoT. For those of you that work on IoT. So then in IoT you have this bunch of devices connected together, billions and billions of them. They are generating data, so that data can also be processed by the phone. I think that's all from my side. Any questions, I'll be happy to answer. I can't hear, I'm sorry. Yeah. So security as such is that we're not looking too much into that. So from this work, all we're saying is that if if the job contains sensitive information, we will not process at the cloud. But as such, there is work where people are looking at the security framework also. So that again is a whole area in itself. I'm sure even if you send to cloud, it can be made secure also. They're not working on that. Yeah, so there is so in the first work we looked at we use iFoxim. So this is I think right there iFoxim. So it's a Java-based simulator, and I think you need Eclipse to run it. With Eclipse you can run it. Otherwise, you can also explore more realistic, like you can get some Raspberry Pis and connect them and hook it up to the cloud, Amazon cloud. That can also. People are doing a lot of. They started doing work, on the smart agriculture, using fog computing. That's cool.
So I would like to extend hearty vote of thanks to everyone who has helped us making this evening successful. First of all, I would like to thank our distinguished speaker, Dr. Nitin Auluck, sir. Thank you so much for the wonderful presentation, and you have made this word lecture very meaningful and interesting. And then I would like to thank Dr. Amandeep Kaur, Dean, SCT, Computer Science and Technology, for her guidance and support. Next, I would like to thank all the faculty coordinators as well as my student coordinators. Thank you for sparing your valuable time. Thank you all for your cooperation. Now please rise for the national anthem. जय